close bracket inverse times b. Alright, so that's how we convert from space back into a transfer function. Okay? So enough about that. We did tell you that for this particular course, we'll be learning about sensitivity functions. Okay, how sensitive is a system to further making. Okay, so in short, there are several tools that we'll use to study the system's response for G, J, omega. And those are basic building block and the microscope. Okay, just a quick look at this. We've gone through this last lecture actually. So you have transfer function GS. Alright, bounded input, bounded output. If you pass in the bounded sinusoidal input, alright, what do I expect? Bounded sinusoidal output. Yes? What has changed? There should not be any changes except that the output will be multiplied by the gain of a transfer function and shifted by the phase. Okay, we covered this last lecture, right? Okay, and if you have a pendular system, we covered this as well. Alright, then we can derive this transfer function. Okay, and this is equivalent to a normal standard second order system. Okay, and you have given the parameters, the model, and put out the transfer function. What can you do with this transfer function? 5 over s squared plus 10s plus 1m the whole 5. Okay, how do you study? Any questions, any comments, any feedback? Anything you want to raise? No? Because I can't be competing with you. Alright? Okay, so the beginning few slides are just a revision of what we have covered last week. Okay? If you work out the transfer function, alright, GS, what can you do with the transfer function? Based on your understanding for dynamics and functional theory. This transfer function, we can draw this plot. Yes? By substituting different values. S equals to j omega, you put in with omega. We can work out the gain and the phase, you can draw a this one. Yeah? Next, what can you do? You can convert the gain into dB. Alright, you can plot the Bode plot. So we are going to plot the Bode plot because there are different ways of pronouncing this. If you go into Google, some people say Bode, there's also Bode, but definitely it's not Bode. You don't pronounce it as Bode. Okay? There are many ways of pronouncing this. Alright, one of the ways is to call this a Bode plot. Alright? So what do you draw for Bode? You draw the gain, the phase. Gain specifically, you often convert it to dB. Alright, and the phase are increased. Or, you can draw a lattice plot. Alright? Which is essentially the plot of gain versus phase. Alright? So if you have a ruler, given a scale, okay, you can find how far it is away from the origin. Draw across. Alright? With a protractor. This one, protractor, yeah, protractor, you can measure the angle. Okay, and you plot the points. Similarly for the other points, and you join them all together. Okay? That's a quick revision on how we do that. So first of all, S equals to j omega. Alright, so we substitute that in. S squared is negative omega squared plus 10 j omega plus 49.5. Alright? Okay? You multiply the denominator by the inverse, and you actually make sure that you have just pure real values in the denominator. You separate with the real and imaginary. Okay, and gain is just the square root of the real part square plus the imaginary part square. And the phase is tangent inverse the imaginary part over the real part. Up to here is still revision. Alright? Okay?
so fast.
Okay, I think recap. We have done an introduction earlier on last week. Okay, we have gone through modeling of continuous time system, differential equation, and space. We have looked at angular model, differential equation, and space. Okay. Next, what we're going to do. Remember that we said that now, from now onwards, we're going to look at the system in this block diagram form. Okay, it's not just C and P, but we also have a pre-filter to shape the reference. Alright, we also want to study how robust is a system when there's external disturbance B and noise. Okay, I will strongly encourage you to take notes instead of making patterns. Alright, because the more you write it down, the more you remember it. Alright, in the exam, I think over a few exams, papers will ask you, you name what are the sequence. Okay? There was another question that said that you know me a phone diagram of a figure of order, figure of freedom controller. Alright, and these are it. Okay, how do you analyze the system? Alright? Error E. E will be the reference R. ES is RS minus YS. The output YS. Yeah? Okay, this is normally what you write down. And normally what YS is ES times CS times ES. Alright, so if we just look at ES itself, it's 1 over CP YS. This is assuming we ignore G and N, okay? So if we ignore the disturbance and the measurement noise for time being, this is what you get. Okay? So if you derive the E, E is R minus Y. Your Y is E times C times P. Okay? With these two equations, you can work out that ES is RS minus E times C times P. Look at ES, so bracket 1 plus CP is RS. Alright? Because ES is 1 over CP or YS, so your 1 plus CP over CP minus RS. Alright? And Y over R is just CP over 1 plus CP. This is ignoring the disturbance B and the measurement noise N. Okay? This is what you learn in dynamics and control. Yeah, without B and N. Alright? Okay? What did you learn in dynamics and control 3? Your transfer function is your feed forward C times P over 1 plus C times P times whatever is your feedback. But there's nothing in feedback. Feedback is 1, right? The gain of the feedback loop is 1. So it's just CP over 1 plus CP. Okay? This is when we do not have disturbance and measurement needs. Any questions? Anybody who's not sure of how we get this? CP over 1 plus CP. Sorry, this is here. Here. This is R. Okay? Alright. Now my question is, okay, now assuming there's no F, no D, no N, this is what I get. Happy. Of course we can't always stay on the same level all the time, right? So what will happen if I tell you ignore R and ignore D? I want a transfer function, output Y and input N. Hand up if you have a question, if you have a comment. Yes? No? This is okay, right? CP1 plus CP, yes? Okay. Now there's no disturbance. Okay, can you write me a transfer function? Output y and input n. Okay? So basically what I'm asking for is this. Alright, we draw the block diagram. Input is n, output is y. Okay? The first n, there's a minus sign here, right? So there should be a minus sign here. Okay? And it goes through CP before it gets to y, right? It goes through CP before it gets to y. All you need to do is to redraw the block diagram without an R, without a D. Okay, and you can work out simply that it's just minus CP over 1 plus CP. Why? Because feed forward over 1 plus feed forward and feed back. Yeah? Okay, so y over n is negative of CP over 1 plus CP. Okay, I will call this CP over 1 plus CP. We call it the complementary sensitivity function. Okay, and we call it T. So T is CP over 1 plus CP. Okay, the next thing you do is what about disturbance. So now, if you ignore R, and ignore N, you want a transfer function between output and disturbance. Okay, all you need to do is redraw the block diagram again. Alright? Okay, so if you want the input to be D, output to be Y, between D to Y is only one straight line, right? Correct? Okay, and the rest is all in the feedback loop. Okay, so between D to Y is one straight line. And the rest is all in the feedback loop. The line sign. As much as possible, I would advise you to draw instead of pictures. Because that will help you register this. Okay? So, you know that the transfer function is the feed forward loop over 1 plus feed forward plus feedback. Feed forward is only 1, nothing. So 1. Okay, over 1 plus, what's the feed forward? 1, feedback CP, so 1 over 1 plus CP. Okay, and we call this the sensitivity function S. We say that CP over 1 plus CP is a complementary sensitivity function T. So T times M. Okay? Why do we call S the sensitivity function and T the complementary? Because when you add that up together, 1 over 1 plus CP plus CP over 1 plus CP, end up with 1. So now that you have separated the system into into three components. With reference to the disturbance, measurement noise, and command reference. How do you look at them together? In your slide. Okay, this is how you get to this. Y equals to 1 over 1 plus Cp times D plus Cp over 1 plus Cp times Fr minus Cp over 1 plus Cp times M. Okay? Alright? In many past exam questions you've been asked about to write down the relationship of the equation relating the output Y to the inputs B, R, and N. And this is the equation we should write down. Okay? Alright, if you simply cannot memorize, if you really cannot memorize, all you need to do is redraw the block diagram to this. Okay? Where your output is Y and input is D. And this, where output is Y and input is N. And you write down the transfer function all over again. Okay? Alright? So we have said that S, which is 1 over 1 plus Cp, is a sensitivity function. It determines the effect of the disturbance on the output. Yeah? Because Y is S times D. Understand that? So if S is bigger than 1, think about it, Y is S times D. So if S is bigger than 1, it means that the disturbance will have a magnifying impact on the output. Yeah? Because the disturbance will be multiplied by something that's more than 1. Okay? Amplified. And T is the complementary sensitivity function. It describes the effect of measurement noise as well as response from the filter reference. Okay, because you see T here on the measurement noise end, and also T on the filter reference. Okay? Alright. Any questions? Okay, if you simply can't see how we have drawn this and this, okay, what you can do is go back home and cover up some of the signals and try to draw it. Here with the input on the left and the output on the right. Okay? Alright. If there are no questions, we'll just move on. If you're copying, don't sigh and hope that I will hear you, okay? Just shout, and wait for always at the end. Because I'm not going to hear you, just hope that I will get the cue. Alright? Now, what have we just covered?
Thank you.
Output Y, okay, is dependent on three inputs.
I see.
Okay? This is the output. Dependent on
Can leave one
P,
gap.
F
Oh,
R, and then
take video.
okay?
Thanks.
F R, very straightforward. Alright, because it's the usual transfer function. Okay, so this is always CP over 1 plus CP. Okay? D. We have drawn the block diagram. So this is D. Okay, between D to Y is one straight line. Alright? The C, the P. Okay? And the negative sign. Alright, P4 over 1 plus prepared. So P4 is 1 over 1 plus prepared. So 1 plus CP. Okay, this is the schema.
Sign, yeah.
Okay? Measurement noise, NS. Alright? On the measurement noise, we go all the way one round to Y, it will pass by C and P. Okay, so we pass by C. I also pass by a negative sign. So that's a negative sign here. Y. Okay. So we have a negative sign because of this negative sign. Okay, CP over 1 plus CP. Okay, all right. I will say that this is S, the sensitivity function. This is T, the complementary sensitivity function. This is also T. Okay. So S is 1 over 1 plus CP. T is CP over 1 plus CP. Okay? And by nature, you know that S plus T is 1. Alright? So let's say, for example, CP is K, P, J, omega plus 1. It is a first order system. Okay? What will happen if omega tends to infinity? Omega tends to infinity for CP as to 0. Because the omega is infinite, right? Okay? How about S? CP tends to 0, 1 over 1 plus 0. S tends to 1. How about T? 0 over 1. 0. CP tends to 0. Omega tends to infinity, CP tends to 0, so 0 over 1. Okay? Right, omega tends to 0. Omega tends to 0. CP tends to K. Right? That's K over 1. K. And we assume that K is quite large, much bigger than 1, let's say. Okay, what is T? T will be K over K, right? Because K is bigger than 1. Okay? K over 1 plus K is K. So this 1. What about S? S will tend to 0, right? Because CP tends to K, and we say that K is very large. Huh? So if you were to draw a plot of S and T, what do you want to see? S, where omega is small, S starts from 0. When omega is large, S tends towards 1. So it goes like that. S goes 1. Yeah? For T, when omega is small, T starts at 1. When omega is large, T tends to 0. T. Okay? Did you understand? If you can understand this, I've got a cue that once you guys start chatting among yourself, you're done. Okay, the reason why I'm writing all of this is so that you understand the slide. Okay, because if you can't understand this, you can't understand the slide. Alright? So if you have gotten this down, at least there's a chance that you still understand the slide. Okay? So the next slide, if you have your notes in front of you, say this. Alright, your open loop gain, L is CP. Okay, so S is 1 over 1 plus CP, so it's 1 over 1 plus L. Okay? P is CP over 1 plus CP, so it's L over 1 plus L. And S plus P is 1. That's a summary. So what happens? Because of the shape of the loop gain L, so if you assume that it's a typical low pass characteristic, this is a typical first order transfer function. Alright, we say that L is CP, which is K over PS plus 1. Okay, so I'm just written K over T, K omega plus 1. So at low frequency, when omega is small, S is small. Okay, so S tends to 0, T tends to 1. At high frequencies, T tends to 0, S tends to 1. This is what I've just written. Okay? Alright? So this is what it is, the loop AL, which is just a pure low order transfer function. It's large at low frequencies and small at high frequencies. And there's a crossover region where L is neither big or small. So we say that L is big. At low frequency, we know that S tends to 0, T tends to 1. But L is small, high frequency, we know that T tends to 0, S tends to 1. Okay? And you know that S plus T is 1. Alright? So there's a trade-off here. Then what do you want to achieve? You want the system to be insensitive to disturbance. Yes? And Y, output Y is S, the sensitivity function, times D, the disturbance. So if my S is 0, Y is 0 times D, is output affected by disturbance? No. So you want F to be 0, yeah? Yes? At the same time, output Y is negative T times N for measurement noise. So if you don't want your system output to be affected by measurement noise, you want your T to be 0. Because Y is 0 times N. There's no measurement noise that will go into the output, yeah? But S plus T is 1. S and T is 0 at the same time? No. S is 0, T is 1. T is 0, S is 1. That's a trade-off. Okay, so what do you want to do? We can have both S and T small. Okay? And we look at our crossover region. Remember, L somewhere near 1. And that is the very critical region, right? So neither S nor T can be small. And it's very crucial to ensure that peaking in S and T is avoided. Because if you have peaking in S, you have disturbance amplification. If you have peaking in T, you have measurement noise amplification. Alright? So it's required to keep the Nyquist plot L far away from the -1 point. Because it's in this critical region where L is approximately 1. Then you need to really, really make sure that your S and T is balanced, is not peaking. So what's the meaning of peaking? This? Okay, any questions from here? Can you actually understand how this relates to what we have just handwritten? Yeah? It's exactly the same. Okay, it's just that that is all in equations and this is all in words. you want to avoid amplifying the disturbance. At the same time, you want to avoid amplifying the noise. Okay? But it's very clear to you that at low frequencies, you are safe because of disturbance. Because S is very small, right? No worries. But you can't do anything for measurement noise. The P is 1. So what do? You must take care of the measurement noise in another way, right? So you might have another filter. Very low frequencies. But at high frequency, okay, I don't really care about my measurement noise because my P is small. Okay, but I have to take special precaution with regards to my S because my S is supposed to be 1. Alright? So if you were to draw a sketch of this phenomenon or low pass characteristic, okay, what you end up with is this. Exactly what we have just sketched. So nothing new. Okay? Nothing new. Alright? The only difference is that this is a dB scale for these two plots. So in dB scale, okay, S was supposed to saturate at 1, and T starts at 1 goes to 0. By dB scale 1 is 0. Okay, because 20 log base 10 of x is 0 when x is 1. Alright, so that's why it ends at 0. Starts at 0 instead of 1. Okay, we'll take a 10 minutes break here.